All right, this is the morning quiz review, Chapter 6.2-6.3, and also covering slope fields. So number one, consider the differential equation dy over dt is equal to t cosine of t squared. Uh, part A is asking to find the particular solution. So in order to do that, we need to first identify the general solution. So to solve, we have to first separate the variables. Let's get the dependent on the left and the independent on the right. So the y's will stay on the left, everything else on the right. We know the left side here, we have dy. Once we take the integral of that, we will simply be left with y. And here on the right side, we have to do a little more work. We have to identify a u value going through u substitution. And the u value is going to be what's inside the parentheses. U is equal to t squared. So we find set our u value to be t squared. Our derivative is du over dt is equal to 2t. Solve for dt, which is du over dt over 2t. We make our substitutions. The t will stay for now. Cosine t squared gets replaced with u, and dt gets replaced with du over 2t. The t's cancel out. We pull the 1/2 as a coefficient, and we know the integral of cosine is going to be a positive sign. Keep the 1/2. We have a plus c. So now we have our general equation. Replace our u value back in terms of t. So we have y is equal to 1/2 sine of t squared plus c. Okay. To find the particular solution, we can plug the ordered pair in for t and for y to solve for c. So square root of pi over 2 gets plugged in for t, and 1 gets plugged in for y. The square root of pi over 2 squared will reduce to just pi over 2. Sine of pi over 2 is 1. 1 times 1/2 is 1/2. 1/2 minus, or 1 minus 1/2 is 1/2. So we have our c value, and we can therefore write our particular solution. Okay, part B. Write the equation of the line tangent to y of t is equal to square root of pi 1/2. So in order to write the tangent line equation, we need the ordered pair and we need the slope. We have the ordered pair, which is square root of pi 1/2. Now to find the slope, we can simply plug our ordered pair or plug in whatever value is necessary into our derivative. And we have our derivative based off of our, is basically our differential equation. So our derivative function, our differential equation takes the t value. So we simply plug square root of pi in for t. So we get square root of pi cosine of square root of pi squared. Square root of pi squared is simply square root of pi. It's simply pi. So cosine of pi is -1. -1 times square root of pi is negative square root of pi. So this is our slope. We have our slope, we have our point. Then we simply plug into our point slope form. So y minus 1/2 is equal to our slope, negative square root of pi, times x minus square root of pi. Okay. Now we're going to use this equation to answer part C. Part C says use the tangent line to approximate 1.3 for the value of t. So we can simply plug in 1.3 in for t, and for my equation I had it in terms of x, so I'm just going to plug 1.3 in for x, and all this can go in your calculator, round to 3 decimal places, so 1.337. Okay, let's look at number 2. The rate of depreciation of a property value y is directly proportional to the value at any given time. So we can write our differential equation based off of this, the sentence here. So it's the rate of a property value, y. So the rate of change of y will be y prime. So we know y prime is directly proportional. We know this is in the form of y is equal to kx. Y prime is equal to k times the value. So value is y. So y prime is equal to k times y. We can write it as dy over dt equals ky. Separate the variables. dy over y is equal to k dt. Take the integral of both sides. We have natural log of y is equal to kt plus c. Exponentiate both sides. We get y is equal to e to the kt times e to the c, and pull the c in front. So we have our exponential decay equation. Y is equal to ce to the kt. Okay, part B. Given that 1960 represents t equals 0 and that it takes 40 years for the property value to decrease by half, find the property value in 1960 if in 1987 the property value is estimated at 125,000. We're going to round to the nearest dollar. So let's identify some of the ordered pairs, some of the information that we know. We know that everything is presented with the independent variable being time and the dependent variable being value. So at any given point in time, there's going to be a specified value attached. So we know that at time 0, basically 1960, we're going to have an initial value which is not provided for us. So we'll just indicate that with C. We know that 40 years later, that the property value will decrease by half. So we'll say equals 1/2 C, half of the initial amount. We also know that in 1987, now 1987 is 27 years after where t equals 0 in 1960. So we know that 27 years later, in 1987, the value will be 125,000. So we start off with y equals ce to the kt. We can't solve for c yet. That's what our final end product, the variable we're trying to look for at the very end. So if we can figure out what k value is, then we can use the other ordered pair to help us solve for c. So we're going to use this ordered pair, 40 and 1/2 c, to plug in and see if we can solve for k. So 1/2 c will replace y. 40 will replace t. Now we see that the c's will conveniently cancel out. We're left with 1/2 is equal to e to the 40k. We want to bring this variable, which is sitting up as an exponent, down. So to do that, we take the natural log of both sides. So natural log of 0.5, I'm just replacing the decimal, the fraction as a decimal. And natural log of e to the 40k, we know that we can bring down the 40k, and natural log of e will just reduce to 1 or simplify to 1. So we have 40k is equal to natural log of 0.5. To solve for k, we divide both sides by 40. So k is equal to 1/40th natural log of 0.5. So now we made progress with our equation. So we can use the other ordered pair that we have, 27, 125,000, to plug in and solve for c. So 125,000 will replace y. 27 will replace the t value. And we're trying to solve for c, and this is just going to be one number, right, that we can all just plug in the calculator. There's no more variables left. So we can take this and divide it to the other side of the equation. So in your calculator, you can plug in 125,000 divided by e to the 27/40th natural log of 0.5. What I did here was I took the 27, put it in the front, and wrote the 27 over 40 as a coefficient. Okay, so we solve for c. C is 199,574.597. We're going to round to the nearest dollar. So 199,575. All right. Number 3, match the differential equation to the correct slope field. Okay. So we have choices in front of us, A through D. So number 3, part 1, we have dy over dx equals negative x over y. Now, we can make a couple of observations just by looking at the property with this differential equation. And one thing that you want to try and pick out some easy information. So if you can find any information about the x-axis and y-axis, those will be the easiest things to spot. Now, you see that there's a y in the denominator, which means that when y is equal to 0, we're not going to get any going to get any slope segments that's going to show up on the slope field. So if y is equal to 0, that's basically the x-axis, right? So we know that the slope is there's not going to be anything that's going to exist on the x-axis. We also know that when x is equal to 0, we're going to get a slope of 0. All right, when x is equal to 0, it'll be maybe 0 over 2 or 0 over 3 or 0 over 4. Anything on where x is 0, we know that we'll get a slope of 0. We know we're going to get a horizontal line segment. So we know that most everywhere on the y-axis, we're going to get a slope of 0. So just based off of these two characteristics, we can narrow down to our solution. We're looking for somewhere that the x-axis does not have anything on it. And we have two choices. We have C, which it's either where slope does not exist or where slope is equal to 0. And we have D, which also has that same characteristic. Now, the other thing that we can look for here is that we know we will get a slope of 0 everywhere on the y-axis. We see that's not the case here, but we do see that is the case here. Okay, and so we know that D is going to be our solution there. Part 2, dy over dx is equal to 0.5y. A couple of observations that we can make is that when y is equal to 0, we know that our slope is always going to be 0. So when y is 0, that is basically the x-axis. So we know that the x-axis will have a slope of 0. And thinking about positive and negative values, the derivative is only dependent on the y value. So basically, anywhere that the y value is positive, so think anywhere above the x-axis, we're going to be expecting positive slope. So positive slope anywhere above the x-axis. And anywhere that the y value is negative, basically any point below the x-axis, we know that we're going to get negative slope. So we can narrow that choice down to pretty much part C. We see that there's a slope of 0. I know it's hard to tell. It's either going to be either slope does not exist at 0 or slope is 0. But the other thing that we can tell is that anywhere below the x-axis, we're seeing everything being negative slopes. Anywhere above the x-axis, we're seeing everything being positive slopes. So we know that C has to be our solution. Okay. Number 4, match the general equation to the correct slope field. Now, the difference here is when you're looking at the differential equation, you are finding some ordered pairs that you can test to see what the slope is. So these individual line segments, we can use the differential equation to find those particular slopes or steepness of each of those line segments. Now, when we're looking at the general equation, we are looking at the overall pattern of that slope field. We're looking at the flow or the general shape of that picture created from the slope field. So basically, if you know what this graph looks like, then you can just look at the shape and see which one will match up. This is going to be a quadratic function. You can plug in the calculator, and it's going to look something like this. Now, C value is a constant. You replace that with any value, 1 or 2 or -1. Now, the only graph that's going to show that characteristic of having a parabola is going to be part B. Okay, so that's our answer there. For number 2 here, C e to the negative x squared over 2. C can be any constant value. Now, we may not know what this looks like, but we can plug in our calculator. And once we do that, we'll have this shape. If we plug in a negative C value, then we'll get a shape that's going to be kind of a half circle on going up. So the only shape that we see that's going to match that characteristic is going to be this slope field here. We see the general shape matching with the general equation when we plug in our calculator.